Yeah, my name is Thomas Ammer, and today we'll talk about the formalization of combinatorial optimization in the Isabelle HOL proof assistant, or to be more specific, I will talk about the formalization of so-called network flows. So just a remark about myself. So I'm a PhD student in computer science in my second year at King's College London. Okay, that's a quick outline of my talk. So I will introduce two types of so-called network flow problems. Then I will move on to algorithms for solving a specific type of network flow problem, the so-called minimum cost flow problem. There will be two simpler algorithms and one more complicated algorithm by Orlin. And then, I will talk about the formalization methodology. And then, because this algorithm by Orlin is still today the most efficient method for solving those minimum cost flow problems, because of that, I will also make a few remarks about the running time. And then finally, I talk about the limitations and how they can be resolved. Okay. So in this talk, I speak about advanced combinatorial optimization in the Isabelle HOL proof assistant. So what's combinatorial optimization? That's an area in discrete mathematics where we aim to find an optimum solution for an optimization problem that is based on some finite structure. For example, a graph. And simple examples for combinatorial optimization would be to find the shortest path in a graph or to compute a minimum spanning tree. Or it could be about network flows. And so what's that? So we have a directed graph, and we want to assign non-negative reals to the edges in that graph. And the intuition is that there's something flowing around in the network. And the edges in the graph have edge capacities, which means this flow that is assigned to an edge should not exceed the capacities of that edge. And then we have two designated vertices, S and T. And now we want to send as much flow as possible from S to T. And for all vertices other than S and T, we have so-called flow conservation, which means the ingoing flow should equal the outgoing flow. And this would be an example for a flow network. So we have a source S, we have a target T, and we want to send as much flow as possible from the source S to the target T while respecting those capacity constraints. And that means, well, the flow that is assigned to an edge should not exceed the edge capacity. And for all other vertices, like those four here in the middle, here, the ingoing flow should be equal to the outgoing flow. And that constitutes a so-called maximum flow problem. Okay, and because the structure is finite, we can compute a solution by means of an algorithm. And now, as you will probably know, all of you, it's very important when talking about algorithms to think about the running time. And strictly speaking, the running time of an algorithm, talking about that, only makes sense when we have a specific model of computation in mind, which could be a Turing machine, for example. And now we say the running time, well, it's the number of steps with respect to a formal model of computation. And yeah, when we think about running time, we always should keep in mind that strictly speaking, running time only makes sense with respect to a model of computation. Well, we say the running time is a term that depends on the input size. We have polynomial and non-polynomial time algorithms, well, which means if the running time is bounded by a polynomial that depends on the input size, then the algorithm is polynomial. And now we want to find algorithms with a good running time. And by convention, that means polynomial running time. And well, the complexity of an algorithm usually implies greater complexity, implies a faster algorithm. That's then the reason for studying complicated algorithms. So that's probably perfectly clear to the computer scientists, but in case you are not very familiar with running time analysis, then you should note that the good running time or the efficient running time of an algorithm is the reason for studying it, although the algorithm might be very complex. Okay. Now, the aims of this work I'm talking about today. So this is part of a bigger project that is done with some collaborators. So we try to build a library of combinatorial optimization formalizations in Isabelle HOL. So we want to formalize graduate and research level theory and algorithms, but there's also some pedagogical intention behind that. And for certain problems, we also want to find executable code, so also to generate code from the formalization. Okay, and for many problems, we give the first formalization of the more advanced bits of the theory, for example, matchings, flows, matroids, or traveling salesperson. Okay, because that's a library, we try to apply a uniform methodology and to avoid redundancy. So the methodology I'm presenting today is kind of representative for this library. And sometimes, well, we also have to reformalize existing things if you want to build a library. And we have some resources on the theory. And the first book on this list, Combinatorial Optimisation by Korte and Wiegand, that's most relevant for what I'm presenting today. Okay, now in case you're interested in that, then this link to the GitHub repository that's also published on the is also published as part of the abstract for this talk. And then there was also a paper at ITP last year together with my supervisor, Mohammed Abdulaziz. So in case you're interested in what I'm presenting today, then please check that out. Okay, what did other people already do? So there was some work on shortest paths in several proof assistants. Then there was Gruskel's algorithm for minimum spanning trees in Isabelle. Then in both Koch and Isabelle, the Gale-Shapley algorithm for stable matching was formalized. And then what's probably most related to what I'm talking about today is the third bullet point on this list, maximum flows. So these were first formalized in MISA by Lee. And as far as I know, this formalization also contained the so-called maximum flow minimum cut theorem, which is important in the theory of network flows. Then there was some work in HOL Light, and then Lamich and Sefitka also formalized maximum flows in Isabelle. And as far as I know, they were the first researchers to have an algorithm in their flow formalization as well. Okay. Now let me get started with network flows in particular. So I already introduced the problem of maximum flows, which means, well, we have a graph, a directed graph. We want to assign non-negative reals to the edges in that graph. Those reals are called the flow. The flow along an edge should not exceed the capacity for all vertices except sources and targets. Well, there the ingoing flow to a vertex should equal the outgoing flow. So this for all ingoing edges, we sum up the flow, and that should equal the sum of the flow along the outgoing edges. Okay, and that's flow conservation. Okay, so that's one version of the network flow problem, and another version involves costs. Okay, so for sending a unit of flow through an edge, we incur costs, and then the vertices can also, let's say, supply flow, or they can be sources of flow. They can also demand flow. They want to receive flow. They can be targets for the flow. And that is condensed into vertex balances. So positive balance means the vertex supplies flow. Negative balance means the vertex is a target for the flow. Okay, so positive balance means more outgoing than ingoing flow. Negative balance means more ingoing than outgoing flow. Okay, in this little flow network, we want to send 8 units of flow from S to T. And for example, this edge pointing from S to V2, it has a capacity of 8. So the flow along that edge should not exceed 8. And the costs are 2. So each unit of flow that is sent through that edge will lead to additional costs of 2. Okay, so now we want to find a flow, well, that satisfies all balance constraints and all capacity constraints. And at the same time, the accumulated costs should be minimized. Okay, and typical applications for that would be to send goods around in a network, for example, or maximum flows could be used to find the maximum number of edge disjoint paths in a graph. I also read that flows can be used for computer vision. So there are lots of applications, but today's talk is about the theory of flows and how that can be formalized. So how can such a flow problem be solved? How can we find an optimum solution? So, well, I think it's not a big surprise if I say that we can improve the solution iteratively. So if let's say we want to solve a maximum flow problem, which means, well, to send as much flow as possible from a source to a target, okay? Then, well, we start initially with the zero flow everywhere, and then we improve the solution iteratively. And now let's try some kind of a greedy approach. So we search for a path leading from the source to the target, along which the remaining capacity is positive. And that would be such a path, for example. Okay, and now we send flow along that path. So let's send 1 unit of flow from S to V2 to V1 to T. And now let's search for another path leading from S to T, along which the remaining capacity is positive, but there is no such path. Okay, so now we send 1 unit of are sending 1 unit of flow from S to T. But this would be a flow assignment that sends 2 units from S to T. So that clearly shows the greedy approach does not work. It does not compute an optimum solution. However, it can be fixed. Okay, how's that done? So from a high-level perspective, one could say the strategy is to make improvements by adding flow and removing flow at the same time. And this will then be called augmentation, which is a primary technique to send flow through the network. Okay, how does that work exactly? So we build an auxiliary graph, the so-called residual graph or residual network. And for any edge in the original graph, we introduce a forward edge to the residual network that points in the same direction. And we add a backward edge pointing in the opposite direction. And now for a specific flow, the notion of capacities can be lifted. So for example, in this flow network here on the left, we are sending 5 units of flow from A to B along an edge whose capacity is 8. Okay. That means the remaining capacity is 3, so we can send 3 units of flow from A to B along that edge, in addition to the 5 units that are already sent. Okay. So, and that's the idea or the intuition behind the residual capacity of the forward edge being 3. Okay. And now, if we want to send flow from B to A, there are 2 possibilities. So what we could do, on the one hand, we could send flow from B to A along this edge. Or we could remove flow that was already sent from A to B. So we could reduce the flow along that edge. And because the flow along that edge is 5, the capacity of the backward edge will be 5 as well. And now when the costs are involved, so the intuition behind a forward edge is to increase the flow along the original edge. And that means the costs of a forward edge should be the same as the costs of the original edge. And because the intuition behind sending flow along a backward edge is to reduce the flow along the original edge, because of that, well, we would save costs, and that means the costs of a backward edge, these should be the negated costs of the forward edge. Okay, and now we say, well, an augmentation means to change the flow that was assigned to the original edges. If we augment by gamma along a forward edge, the flow along the original edge is increased by gamma. If we augment by gamma along a backward edge, the flow along the original edge is reduced by gamma. Okay. And then in this residual graph, which is an auxiliary graph, we can also form paths. And a path with a positive capacity everywhere is an augmenting path. Augmenting along a path means to augment along each edge that is contained in that path. And now one can prove something for maximum flows, which is a characterization. When is a flow sending units of flow from S to T a maximum ST flow? Okay, and that is the case if there is no such augmenting path. Okay, so recall that the characterization or the characterization by absence of paths in the actual graph with a positive remaining capacity did not work. But when having this residual graph and the notion of residual capacities in there, then flow maximality can be characterized by the absence of paths. And that's something very significant, and that's part of the so-called Max-Flow-Min-Cut theorem, which is central to the theory of flows. Okay, and when costs are involved, we say an augmenting cycle is a closed augmenting path with negative costs. So, and then when the costs are involved, again, we can show something about the effect an augmentation would have on the flow. So we say we can show that if the flow F is augmented along an augmenting path P by the value gamma, then the costs of the resulting flow F prime will be the same as the costs of F plus gamma times the residual costs of P. And then one can prove a second characterization. So one can show a flow is a minimum cost flow if it does not allow for an augmenting cycle. And those results on that slide here, the two characterizations of flow optimality, on the one hand for maximum flows, on the other hand for minimum cost flows, and also the effect an augmentation has on the costs. All of these were formalized in the Isabelle proof assistant. Okay. And now we can exploit this idea of augmentation for algorithms. Okay, so from a very high level perspective, we could say, well, augmentation is used to improve a solution iteratively. And then in the end, flow optimality will follow from those characterizations. For example, now we think about minimum cost flows, and that means in the end, the final flow should not allow for an augmenting cycle. And by this characterization, this implies that the flow is optimal. And now there are two ways of using that. On the one hand, one could repeatedly use augmenting cycles, augment the flow along these until there are no such cycles remaining. By the characterization, this implies optimality. Or one could use shortest paths, which means, well, we augment flow from sources to targets along minimum cost augmenting paths, okay, along the cheapest possible opportunity. And then this will also lead to an optimum solution. And although it's not immediately obvious, the optimality criterion is again involved in this kind of algorithms. And today I will present three algorithms, and all of them belong to the second class. So all of them are shortest path algorithms. Okay, so the simplest algorithm would do the following. It would take a source, which means positive balance. It is supplying flow. It would take a target, which means negative balance, a vertex that is demanding some flow. And then it would find a minimum cost augmenting path leading from the source to the target. Then we would augment along that path P by some value gamma. And then because some parts of the supplies and demands in the network have been matched to one another, because of that, well, the remaining supply and demand is less. So the supply and demand at S and T respectively needs to be decreased by gamma. Okay, so this algorithm is already correct, although the running time is bad. So why is this algorithm correct? So we have two invariants. So in case somebody doesn't know, an invariant is a property that is always true at a certain line of the program, or it can also be seen as a way of performing an induction over a loop execution. So we have two invariants. And the first invariant is not that interesting. It just says the capacity constraints are always satisfied. The second invariant is the important one. It says the current flow F does not allow for an augmenting cycle. And now in the theory of flows, there's this theorem which says that if a flow does not contain an augmenting cycle, or if it does not allow for an augmenting cycle, and if this flow is augmented along a minimum cost augmenting path from some source to some target, and that results in F prime, then this flow F prime will not allow for an augmenting cycle either. And this theorem, that's the major correctness theorem that is used to prove all algorithms I'm talking about today correct, and bringing that into a state such that it could be formalized was a considerable part of our efforts. because there's some interesting or some complicated graphical argument in there. And graphical arguments are always difficult to formalize. Okay, so this algorithm then is correct because finally all flow would be distributed. So there would be no remaining supply and no remaining demand. And then because of this invariant, well, the final flow will not allow for an augmenting cycle. And because of the characterization of flow optimality, the final flow will indeed be a minimum cost flow. And now all algorithms I'm talking about today use this correctness argument, but the algorithms I will talk about later, these will be more efficient than this one. Okay, so why is the running time of this algorithm bad? Okay, so suppose we want to send 8 units of flow from S to T and the gamma value is 1. Well, then we would send 1 unit of flow from S to T, then we have balances 7 minus 7. Another unit, its balances 6 minus 6. Another unit, its balances 5 minus 5. So we would need 8 augmentations. Or in general, we would need a number of iterations that is linear in the sum of the absolute values of the balances. And that is a very, very inefficient algorithm, because if the numerical values of the balances are very large and the network is small, then we can wait for ages. Okay, so how can that be made more efficient? What we do is we use so-called capacity scaling. Okay, and now this algorithm has some restrictions. So we need to assume infinite capacities, and we also need to assume integral balances. I will later show how that can be removed. Okay, but the idea behind scaling is to pick those sources and those targets that have a high supply and demand, and then we can send lots of flow from the source to the target, and that allows us to make a fast progress. Okay, in fact, it does not have to be a source or a target with the highest possible supply or demand. It's enough if we pick sources and targets with sufficiently high balances. And that means a balance that is above a threshold. And in this case here, we use gamma as the threshold. And please recall, gamma is also the value by which we are augmenting. Okay, so this is a capacity scaling algorithm to solve the minimum cost flow problem. Of course, we can't discuss this algorithm in detail, but let me make a few high-level comments. So we have an inner loop, and this inner loop selects those sources and those targets where the balances are above gamma, and then it sends gamma units of flow from such a source to such a target along a minimum cost augmenting path. And if there are no such sources and no such targets remaining, then the gamma value needs to be halved. Okay, and that's the idea of scaling. So we have this threshold that determines whether a part of the problem is interesting. And if it is interesting if it is worthy of being treated now, then we send lots of flow from that source to the target, which means, yeah, we treat this part of the problem. And by that, we make a much faster progress. Okay, so in an example again, so if the gamma is 4, and again, we want to send 8 units of flow from S to T, okay, then is there a source and a target with a balance above 4? Well, yes, it's S and T. Okay, so let's send 4 units of flow from S to T. Now, is there a source and a target with supply or demand above 4? Well, no, so the gamma needs to be halved. Now we can again send 2 units of flow from S to T, and then gamma needs to be halved again because there's no source and no target remaining with a balance above 2. And finally, we can send the last 2 units of flow from S to T. Okay, although that might seem like a small difference, in the end, it will make a big difference because now we need only 4 augmentations, and that's the binary logarithm of 8 plus 1. And in general, we would need a number of iterations that is linear in the binary logarithm of the sum of the absolute values of the balances. And that is a much faster algorithm. Okay. Now, this can be made even faster and that will lead us to Orlin's algorithm. Okay, so the central idea behind Orlin's algorithm is to concentrate balances, so which are supplies and demands at certain vertices in the network. That will again be done by means of an augmentation. Okay, now so I will now give a few remarks on how that can be done. Again, I don't think it's necessary to understand any detail in there. Just so my main intention is to give you at least some high-level intuition about how this algorithm works. So what we are doing now is we build a graph of edges that carry a comparably high amount of flow. Okay, so there's another auxiliary graph, and that will be a forest. And now we perform concentration, which means, so the forest is grown, and that means the number of components is reduced. Each forest component has its own representative, and only representatives are allowed to have non-zero balance. And then the intuition behind that is to contract edges that carry a high amount of flow and to identify the respective endpoints. And that would mean certain edges disappear, but we do not want to perform this contraction explicitly. So what we have to do is we have to deactivate certain edges. And then they cannot be used in any subsequent iteration. And the flow along those edges will be frozen. Okay, so here in this network, we send 9 and gamma units of flow from X to Y to Z. And for the algorithm, that would be a comparably high amount of flow. So an edge needs to be added to the forest. And for example, it could be this edge pointing from Y to Z. Okay, initially, all vertices are their own forest components. So all vertices are also their own representatives initially, but now we have a new forest component and Y is selected as the representative of both of Y and Z. Okay, but the balance needs to be concentrated at a single vertex, the representative, which is Y in that case. Then there's another edge that can be added to that forest. And then X is selected as the representative, and all the balances are concentrated at X. And all other vertices are zeroed. And this edge here, because if we would perform contractions of the red edges explicitly, this edge here, pointing from X to Z, would disappear. But we don't perform that explicitly. Because of that, the edge has to be deactivated and it cannot be used in any subsequent iteration. Okay, why is that a good idea? That will be a good idea because the sources and targets in the network need to be representatives. And the number of representatives is reduced because the forest keeps growing. And in fact, one can prove by an involved argument that the time between component merges will be polynomial in the number of vertices and the number of edges of the graph. And because the number of vertices is n, there can be at most n merges. And that means the number of augmentations will be, again, linear in some polynomial that depends on the number of vertices and the number of edges. And what's interesting about that is that the numerical parameters of the problem, the costs, the balances, and the capacities, these don't play a role anymore in the running time. And that's what makes Orlin's algorithm pretty significant. So this idea of having this forest where we have components with representatives and balances are concentrated at representatives, that reduces the number of times when we have to search for a source, for a target, and for a path. That's a considerable improvement. The good thing about Orlin's algorithm is that it can deal with real valued balances in contrast to the capacity scaling method, where the balances need to be integral, but still the capacities need to be infinite. Okay. Now, Orlin's algorithm is pretty involved, so this pseudocode fills an entire slide. Of course, you don't have to understand that in detail, but just let me make a few high-level comments. So we have an outer loop that is responsible for maintaining this gamma value. Then we have an inner loop here, which sends flow from sources to targets, and the balances of the source and the target that are used have to be big. And whether the balance is big, that depends on the threshold value gamma. And then if there are no sources and no targets remaining that have lots of supply or demand, then the gamma is halved. And after that, this balance concentration thing is performed and the spanning forest is grown. Okay, so you see Orlin's algorithm is pretty involved, and formalizing and verifying such a method in a proof assistant is really a non-trivial task. Okay, how can that be done? So the loops are the most important control structure here are formalized as recursive functions. And then the algorithms work on program states, which are collections of variables. So for example, a program variable would be the current flow. And those program states are formalized as records, functional records, as they are provided by the Isabelle language. And then, the loops are modeled as functions that map the program state at the beginning of that loop to the program state immediately after finishing the loop. Then loops are verified by invariants, which are properties that are always satisfied at certain lines of the program. And the most important invariant here is, please recall that the current flow does not allow for an augmenting cycle. And that, that can be seen as a way of performing induction for program verification. And then the algorithms, they make use of sub-procedures, for example, to select minimum cost paths. At least now, we do not want to restrict ourselves to a specific sub-procedure, to a specific implementation of path selection, for example, Bellman-Ford or Dijkstra or whatever. Instead, we just assume sub-procedures and we use them in a black box manner. And that's done by means of locales, which are contexts. Okay, and then also later, maybe we want to obtain executable code. And then we have some problem with mathematical entities like ordinary mathematical sets that are used in the program state. And later that would have to be then replaced by some implementation, some suitable data structure. And so we try to do that right now. But again, we do not assume a specific implementation for sets, for example. We just assume the behavior good set implementation should have. And then based on those assumptions, we formalize Orlin's algorithm. Okay. So, and that concept is called abstract data type. Okay, so that's an example as an example of how a loop can be formalized by a recursive function. This is not Orlin's algorithm. Instead, it's depth first search, perhaps the simplest graph algorithm one could imagine. Okay, and if I would display Orlin's algorithm on the slides in Isabelle, then this would take at least 5 slides, perhaps even 7. Okay, now how can we deal with sub-procedures? So that's a locale that specifies the behavior of sets. So that's taken from the standard Isabelle distribution. Okay, so what we have is for example, an insertion function that has a specific type, and it has certain properties. And those properties here, this single statement specifies how a good set implementation should behave. And then in the body of the context, we can use those properties. And for more complicated sub-procedures, for example, path selection, you can do the same. You can assume a name, you can assume a type, and then you can specify the properties, and you can use the function in a black box manner. And later, the assume functions, the abstract data type operations, but also path selection procedures can be instantiated by suitable implementations. Okay. Now, central to that is the idea of stepwise refinement, which means we have a program that consists of instructions. and then those instructions are replaced by more detailed instructions. For example, we say we want to select a path, but we assume that in a black box manner, and then this is replaced by some implementation later on. Then we also have abstract data types, which means we just specify the behavior a set implementation, for example, should have, and later we give implementations for that, for example, red-black trees, but we just work with the specification, and based on that, we perform all our proofs. And then other authors used locales for stepwise refinement as well. So the work I'm presenting here is not the first example for that. Okay, so Orlin's algorithm is pretty significant because it's the fastest method to solve the minimum cost flow problem still today. It's even strongly polynomial, so that means it's polynomial in the number of vertices and the number of edges of the graph. And the proofs are pretty sophisticated. For example, a considerable part of the proofs in the textbook by Kort and Wiegand are busy with discussing the running time argument. And so we decided to formalize this running time argument as well. And so how can that be done? So the algorithms, including Orlin's, were formalized as Isabelle functions. And these are timeless, they are purely mathematical. So what we then need is we need to define a notion of time on our own. And right now, we don't want to go for a formal model of computation. Instead, we want to define some more, not really informal, but a more a simpler notion of time. And that means we define functions that resemble the structure of the algorithm while summing up natural numbers. And then those numbers should be then a measure for the running time with respect to a formal model of computation. Okay, and then for a much simpler algorithm, merge sort, for example, you could say that the time we need to sort n elements is the same as the time we need to twice the time we need to sort n over 2 elements plus constant times n. And the same approach works for Orlin's. Although we will have 3 functions because there are 3 loops, and each of those functions will be much more complicated than the one displayed on that slide. And then because Orlin's algorithm makes use of sub-procedures for path selection, and we have to assume times for these as well. Okay, so we also then assume natural numbers whose meaning is the running time of the respective sub-procedure. Okay, and now those times are incorporated into the times we need to execute a loop body once. An example in a minute. So, and that's a variation here of an approach by Nipkow and others. Okay, so that's the running time function for the top level loop of Orlin's algorithm. And so what it's doing, so it takes a program state and then it returns a natural number, which should then be a measure for the running time with respect to a formal model of computation. And on the other hand, it returns the final program state. Okay, so in here, we have those 2 functions, loop A time and loop B time, which are the running time functions for the lower level loops. And then we have a recursive call. And overall, that resembles the structure of the loop that models the actual algorithm. Okay. And now in the end, so we take this running time function and we plug the initial program state into that function, and that yields a natural number. And then this number, T Orlin's, can be bounded by the term displayed on the right-hand side of this inequality. And on the one hand, we have the n, the l, and the k, which are all depending on the size of the graph, because n is the number of vertices, m is the number of edges. And on the other hand, we have those t's, which are times that we need to execute basic parts of the program. For example, the time we need to check a loop condition once, or the time we need to execute a loop body once. And that includes the time for path selection. And because those times here are just assumed, and because the fact that those functions we defined model the running time of the algorithm, because that's only visible to the Isabelle user at an informal level. Because of that, the argument that was formalized is more kind of semi-formal. So the interesting stuff, or the more complicated parts of the argument, were formalized, but the fact that this is a running time bound for Orlin's algorithm, that's only visible at an informal level. Okay, now if we would perform big O analysis just for the sake of completeness, this big O expression here is an asymptotic bound for the number of iterations, or the number of augmentations, when we have a graph with infinite capacities. Then, depending on which algorithm we use for path selection, then this will result in one of those two running times here. And the interesting thing is that the numerical parameters of the flow problem, the costs, the balances, and the capacities don't play a role. It's just the size of the graph what matters. And that makes Orlin's algorithm pretty advanced. Okay, now this algorithm has some limitations. So the first limitation comes from the central invariant, which says there is no augmenting cycle. Okay, initially, the residual graph is essentially equivalent to the actual flow network. So the flow network should not contain negative cycles. But of course, there might be networks that have negative cycles. And then Orlin's algorithm assumes infinite capacities. But of course, there might be problems where the capacities are finite. So that means other problems need to be reduced to that setting. And what we then do is we apply some trick, and we replace finite capacity edges and change the network a little bit. And then one can show, and that proof is of course also formalized, that for any flow in the old network, there will be a flow in the new network and vice versa. One can also show the new network will not contain a negative cycle if the old network does not contain a negative cycle that has infinite capacity. Okay, so to solve a flow problem now with finite capacities, we need to transform the network. We then compute a flow in the new network, and then the flow is transformed back into a flow in the old network. Okay, the blow-up is linear. One can show that. And then this means that Orlin's algorithm is a fastest method for the minimum cost flow problem in general graphs, irrespectively of whether the capacities are finite or infinite. Okay, now a few technicalities. So this reduction requires multigraphs, and the formalization had to be changed because of that. So just in case you don't know, so a multigraph is a graph where we have multiple edges between vertices. And then this is formalized as a set of objects together with two operations, first and second, that return the respective endpoints. And notably, the algorithms are not affected, and adjusting the formalization to multigraphs just took me approximately 2 hours. So although that sounds like a big change, it really wasn't. Okay, now other things you can do when working with multigraphs. So you can reduce the maximum flow problem to the minimum cost flow problem more easily. You can prove so-called flow decomposition, another important result from the literature, more easily. Then you can show things like there is an optimum flow if the flow problem is feasible, so if there is a solution, and if there is no negative infinite capacity cycle. And then in the end, we also obtain verified functional code for minimum cost flow problems for arbitrary capacities. So the capacities can be reals or they can be infinite. And also we obtain verified code that solves the maximum flow problem. In the background, Orlin's algorithm is used. Okay, let me quickly summarize. So I formalized the minimum cost flow problem, which belongs to combinatorial optimization. So in total, that's 35,000 lines of proof. Then for solving the flow problems, we used the augmentation technique, which is a way of sending flow through a network. And then there are characterizations of flow optimality. So a flow is optimum if and only if there is no structure that allows for an augmentation. Then to obtain a fast algorithm, one can use the idea of scaling. That means to pick big parts of the problem first and make fast progress. Then another idea how a flow algorithm can be made faster is concentration of balances. That leads to Orlin's algorithm, which is quite complex, and that was formalized. Then central to the formalization methodology, especially when it comes to obtaining executable code and instantiating assumed subprocedures, is the idea of stepwise refinement. Then we have a semi-formal running time argument that formalizes the interesting parts of the proof in the literature. And then we formalized reductions among flow problems, and that required multigraphs. Okay, thank you very much. That's it.
Thank you so much, Thomas, for giving this talk. Do we have questions?
Sorry, I can't hear you.
Oh, could you not hear me?
I can. Now I can.
Okay. I was just thanking you for giving this talk, and I was asking the room if there are any direct questions. If not, then I have a question. Namely, you said
Sure.
that you wanted all your algorithms to be executable. Did you try executing them? So did you have some examples?
Benchmarks?
Yeah.
No, we don't. At least not yet.
Okay, but so you didn't have benchmarks, but did you have like a single problem where you tried?
Yes, we do. We do have that. But we did not conduct any time measurements.
Okay, sure, yeah. But that's a plan for the future?
It's at least an option for the future. Maybe we do that, maybe we don't. I don't know yet. But at least for some problems, we would like to have that at a later stage. But right now, the main focus is the mathematics.
Okay. Let me see in the chat if there are any questions there.
Where's that?
Okay, yeah.
For the abstract data types, have you ever done anything to do with associating with them, the sets thing you showed?
I mean, if not, I can repeat the question.
But is it have you heard what I'm saying?
Thomas, could you hear the question?
Not clearly.
Probably easiest. Okay.
So you talked about abstract data types, and you had that example of a set.
Yeah.
With any of those, do you have associated runtime things? So you
I think for those, at least for certain set implementations, I think there are running time proofs using the same methodology as we do, but that wasn't our work, so I don't know a lot about these. But there are some implementations satisfying the set specification, for example, where there are running time proofs.
Okay. I mean, you can do sets very fast when you use hash maps.
Yeah, for example.
You didn't actually implement that, but you just adjusted the function so that it would represent some optimized way of dealing with sets.
So actually, we are using red-black trees because that was the easiest thing. But later, when we might go for executable or more efficient executable code, then using hash maps might be an idea. So, but right now it's just red-black trees.
Oh yeah, but actually then you lose something on the formal side because you might have collisions.
Yeah, and then this needs again verification. So at least right now it's best to stay simple.